July 10, 2026. A billion-dollar mission is plunging through heavy ocean fog, seconds away from hitting the water. At this terminal velocity, a miscalculation of even a few centimeters results in the immediate loss of the hardware, the payload, and years of scientific momentum. Before this impact occurs, we need to examine how a space program that lagged behind its rivals managed to reach this specific point of technical risk. This is a demonstration of capability, intended to prove that the logistics of orbit are no longer a Western monopoly. Surviving the final few seconds of this freefall would confirm a new technical parity in heavy-lift aerospace. For over half a century, the United States maintained the lead in orbital logistics. That lead was built on achievements in off-world landings, setting a mechanical standard that remained unmatched for decades. Throughout the 1960s and 80s, the Chinese space program operated with significant technological delays and limited access to high-performance computing. Catching up involved a multi-decade industrial grind, often relying on the adaptation of older, bulkier manufacturing techniques. Even with the arrival of reusable rockets, the capability for vertical recovery remained confined to American private enterprise. To bridge that gap, China targeted a more complex environment. This diagram compares a stable land target with an ocean platform, which is constantly pitching and rolling while subjected to shifting, intersecting wind vectors. Time unpauses. The engines ignite in reverse, generating thousands of pounds of thrust to push back against the atmosphere. The thermal and kinetic loads during this rapid deceleration are severe enough to compromise the structural integrity of a standard rocket fuselage. To withstand the descent, this engine technology is designed to reliably reignite while the vehicle is falling backward at supersonic speeds. Internally, the fuel systems have been modified to prevent fuel slosh, ensuring a continuous flow of propellant despite the violent forces of the braking maneuver. Most traditional rockets avoid these stresses by breaking apart and burning up in the upper atmosphere. Controlling the speed of the fall is only the first requirement. The next is managing the unpredictable environment of the open sea. As the rocket slows, high-altitude wind shear actively pushes the airframe off its vertical axis. An onboard AI system must process chaotic environmental data faster than a human operator could react. Simultaneously, sensors calculate the exact movement of the sea swells, shifting the platform below. These micro-adjustments occur thousands of times per second, allowing the flight computer to counteract wind interference in real time. Those calculations result in rapid gimbal movements. The engine nozzle tilts continuously, steering the falling mass toward the center of the platform. In the final 10 seconds, the hover phase, the vehicle requires centimeter-level precision to touch down without tipping. While the engines provide the force for the descent, the AI provides the coordination necessary to land on a moving target. Engine cutoff. The rocket settles on the platform. For the engineers in the control room, this represents the culmination of a decade of development and testing. This successful recovery integrates complex propulsion, guidance, and automated control systems into a single functional operation. By duplicating one of the most difficult feats in aerospace, China has ended the era of a single-nation monopoly on sea-based rocket recovery. The mechanics used for this landing have applications that extend far beyond Earth's atmosphere. Establishing permanent bases on the Moon or Mars requires heavy payload vehicles that can touch down with this same level of precision. Managing the variables of Earth's oceans provides the control framework needed to handle the thin atmosphere of Mars or the uneven terrain of the lunar surface. Recovering rockets at sea lowers the cost of every subsequent flight, shifting space exploration from a series of individual events toward a sustainable cycle of transport. Picture a 50-meter steel tower falling from space, aiming for a small, moving platform in the middle of the ocean. For decades, the standard procedure for orbital launches was to discard the hardware. The massive bottom section of a rocket, the booster, would fall into the sea and sink after a few minutes of work. This chart shows the disparity in launch economics. The tall bar represents the tens of millions of dollars required to forge a brand new booster. The tiny bar next to it represents the cost of the propellant needed to refuel an existing one. Throwing away that hardware capped the frequency and ambition of space programs. To build large-scale infrastructure in orbit, launch vehicles must operate with the repetition of commercial aircraft. To achieve that, the booster performs a complex maneuver. Once it separates from the upper stage, cold gas thrusters flip the cylinder backward in the vacuum of space, turning it into a self-guided dart. It doesn't usually head back to the launch pad. Carrying enough fuel to reverse course completely would reduce the rocket's payload capacity. Instead, it rides a parabolic arc out toward the open sea. The oceanic recovery is the specific engineering solution that makes space travel a repetitive industrial cycle rather than a series of expensive one-off events. The first physical barrier the returning booster encounters is the Earth's atmosphere. It hits the thickening air at hypersonic speeds, traveling thousands of meters per second. At that velocity, the air cannot move out of the way fast enough. The intense compression creates a sheath of superheated plasma, pushing temperatures on the leading edge of the grid fins and engine bells into the thousands of degrees. If the descent rate isn't checked, the structural integrity of the aluminum-lithium hull will fail from thermal stress, or the vehicle will shatter upon impact with the water. Survival depends on reigniting a subset of the main engines while falling backward through a supersonic slipstream. The computer must trigger the ignition fluid at exactly the right altitude. A fraction of a second of delay guarantees a high-speed collision with the ocean. Clearing the thermal gauntlet and executing a successful entry burn simply slows the hardware down. It only buys the vehicle the chance to find its final target. As the target comes into range, the flight computer takes over. It ingests radar altimeter data, calculates wind shear, and maps GPS coordinates. The system actuates titanium grid fins to steer the base, adjusting the glide slope on a millisecond basis with superhuman precision. It is aiming for an autonomous spaceport drone ship, a heavily modified barge waiting at specific coordinates hundreds of miles offshore. Landing on solid ground requires matching velocity to zero, but the open ocean is fluid and chaotic. The target faces massive, unpredictable swells. To combat this, the drone ship is equipped with azimuth thrusters. These dynamic positioning engines constantly rotate and fire against the current to keep the steel deck locked onto a specific location. The final maneuver demands exact synchronization. A 50-meter cylinder has to meet a deck that is pitching and rolling in 3 separate dimensions. It is a live physics calculation where altitude, wind speed, and the ocean swell shift continuously right up to the moment of impact. In the last 10 seconds, the final landing burn engages. The raw thrust from the engine violently displaces the ocean water, creating a dense cloud of steam as the landing legs deploy. The exhaust cuts off, the smoke clears, revealing the charred booster standing vertically on the deck, secured for its return to port. Because the booster survives, the financial structure of a launch changes. The cost of the hardware can now be spread across multiple missions, significantly lowering the barrier to entry for orbital payloads. Lowering orbit access costs makes expansive new projects viable. The industry shifts from launching isolated satellites to deploying internet megaconstellations and modular space stations. This efficiency supports the goal of establishing permanent outposts on the Moon or Mars. It enables the consistent, high-volume shipping required to transport the heavy machinery and supplies needed for survival. This engineering benchmark has set a new global standard. Expendable launch vehicles are becoming obsolete, and aerospace agencies worldwide are rushing to adapt. The landscape is expanding from a few commercial pioneers to heavy competition with state-backed programs, particularly as China accelerates its development of reusable launch systems. The physics of the ocean landing have been solved. Now, the nations and corporations racing to scale this capability will dictate the logistical pathways of the inner solar system. Watch the final seconds of this descent. The engines throttle against their own momentum, balancing a multi-ton cylinder of metal on a pillar of fire in the middle of the ocean. The mid-century space program relied on brute force. A Saturn V launch burned through millions of pounds of propellant just to discard its massive stages into the sea, treating precision engineering as disposable hardware. Recovering a falling booster changes the financial math of Aerospace. When the vehicle is no longer thrown away after a single trip, the capital required to leave Earth drops to the cost of propellant and refurbishing. This shift toward reusability has accelerated a dormant industry. Reaching orbit is now a high-frequency operation. turning scientific exploration into a rapid, high-stakes competition. The old rivalry between Washington and Moscow was a strictly government affair. Today, the geopolitical landscape is more crowded and less predictable. Commercial entities now drive the development timeline. Companies like SpaceX build, test, and fly hardware with a rapid cadence that older aerospace contractors struggle to match. These private companies are racing against vast national resources. China's state-backed program is expanding its infrastructure, deploying modular space stations and testing new heavy-lift capabilities at an aggressive pace. We now see agile corporate engineering competing with limitless sovereign wealth. This combination makes the current sprint to orbit faster and more volatile than it ever was during the Cold War era. A completely redesigned approach to rocket architecture now dictates the pace of both global competitors. This chart compares traditional mission costs to a reusable model. By landing safely, expensive hardware is preserved. Returning boosters rapidly increases mission frequency. Flights requiring months to manufacture now rely on a refueling cycle taking only days. To survive these repeated trips, a vehicle has evolved. A modern launch vehicle functions as a flying supercomputer capable of autonomous decision-making. Onboard software processes thousands of telemetry data points every second during the ascent. During descent, autonomous systems adjust grid fins and engine gimbals with microsecond precision. These calculations are impossible for human pilots to execute in real time. Digital simulation models identify structural limits before hardware is ever built, reducing the number of real-world test failures. Advanced software and automated control have become the primary barriers to entry. In this race, the ability to operate complex autonomous systems determines who reaches orbit and who stays grounded. As the path to low Earth orbit becomes routine, the strategic focus has moved to the lunar surface. The modern objective is a permanent presence. Current programs focus on building infrastructure for resource extraction and long-term human habitation. A functional lunar base acts as a staging ground for deep space. Because the Moon has significantly lower gravity than Earth, it provides a much more efficient point for launching heavy payloads to other planets. This makes the Moon a critical hub. Establishing refueling and supply chains there dictates transit routes for the rest of the solar system. Mars represents the current limit of human engineering. It is the final testing ground for self-sustaining survival off-world. Reaching the surface requires navigating an atmosphere prone to global dust storms and extreme temperature shifts that can compromise mechanical systems instantly. Safely landing a crew there requires perfecting the autonomous entry protocols and closed-loop life support systems currently being refined on the Moon. Planting a permanent flag on Mars will require solving the final, most complex variables of deep space transit and biological survival. The immediate economic impact of this race is happening much closer to home, within Earth's immediate orbit. Dropping launch costs have initiated a commercial expansion, allowing private companies to maintain thousands of small satellites in low-altitude clusters. This animation shows our globe encased by interconnected nodes. Each launch adds to a dense web of global communication hardware. These nodes connect directly to the ground. They synchronize stock market trades, route military logistics, and guide autonomous shipping through international waters. While deep space dominates the headlines, the immediate victory is logistical. Controlling the path to orbit means controlling the physical backbone of the modern digital economy. Space has matured into a foundational pillar of human industrial infrastructure. Within our lifetimes, off-world transit and orbital logistics are positioned to become as routine and commercially reliable as standard international aviation. As superpowers and corporations push the boundaries of engineering, we are left looking back at our starting line, waiting to see where humanity settles next.
If all of our critical orbital infrastructure vanished today, modern life as we know it would instantly collapse. Thousands of active satellites currently trace complex paths over our cities, forming a massive, invisible network that powers our global economy. Look at how this data moves. Our daily GPS navigation, weather forecasting, and the precise millisecond timing required for global financial markets all rely on these orbital nodes communicating with surface stations in real time. Our activities in space have transitioned from scientific curiosity to a requirement for our survival. we have built a celestial infrastructure that we cannot afford to lose. Despite the success of this network, humanity remains largely trapped in low Earth orbit. Two specific pressures are forcing us to look further out. Earth possesses a strictly finite supply of critical resources, and the orbital lanes closest to our atmosphere are rapidly becoming overcrowded. To maintain our economic trajectory, we must transition from being temporary visitors in space to permanent residents. Right now, low Earth orbit is a bottleneck. Building a physical stepping stone deeper into the solar system is the only way to guarantee the long-term security of our species. The Moon serves as a necessary industrial zone where we can test the logistics of long-term survival before moving further out. International space agencies are currently mapping these craters to establish permanent, year-round research stations on the lunar surface. A primary objective for these bases is resource extraction. Robotic systems are being designed to harvest materials directly from the lunar soil, specifically targeting trapped water ice. Processing these resources on-site provides the fuel and life support reserves necessary for deeper missions. By producing propellant off-world, the Moon effectively becomes a cosmic gas station. Mastering these extraction techniques is a prerequisite for any mission attempting to reach Mars. Historically, the cost of leaving Earth's gravity well has limited our reach. The massive financial and logistical barriers of single-use rockets kept deep space missions rare. Reusable rocket technology reduces the cost of leaving the atmosphere. By landing and relaunching this same hardware, we can finally make deep space travel economically viable. But reaching the next planet introduces a new problem. As ships travel millions of miles away, the delay in communication with Earth can stretch into several minutes. To solve this, mission designers are integrating artificial intelligence and autonomous robotics. These systems are capable of making split-second, life-saving decisions without waiting for instructions from mission control. The combination of affordable propulsion and autonomous intelligence is the engine that makes the next stage of spaceflight possible. These engineering solutions are aimed directly at Mars. This landscape represents the primary target for the first human colony beyond the Earth-Moon system. Establishing a foothold here requires overcoming severe cosmic radiation, multi-month transit times, and the complexities of maintaining a closed-loop life support system. To protect the crew, designers are drafting blueprints for shielded habitats, while autonomous drone swarms are being developed to prepare the landing sites before humans arrive. Beyond the technical challenges, astronauts will face extreme psychological isolation, operating with the knowledge that Earth is millions of miles across the void. When we successfully establish a self-sustaining presence on this soil, humanity officially becomes a multi-planetary species. Mars is a stepping stone for human curiosity. Our drive to understand the universe extends far into the deep space nebulous beyond our solar system. Long-term plans include missions toward distant exoplanets and asteroids, where we can study the composition of the universe at its most extreme. The scientific data gathered by these probes helps us reconstruct cosmic origins and look for biosignatures that might indicate the presence of other life. Navigating this interstellar void is the ultimate goal of our expansion, allowing us to answer our oldest existential questions. This expansion into the cosmos relies on the work being done on Earth today. Deep space missions require massive international cooperation, utilizing the combined scientific and financial resources of multiple nations. The success of these missions depends on the next generation, the students and engineers who are currently designing the propulsion systems of the future. The technical foundation for a multi-planetary civilization is being built in laboratories around the world right now. We are reaching the point where populating other worlds is a technical objective rather than a distant dream. The remaining questions concern the timeline of our expansion and which nations will coordinate the move towards the stars.
Thousands of years ago, early humans stood at the edge of the water, built crude vessels, and pushed out into the treacherous oceans. Today, we stand on the shores of a vastly larger, darker ocean, preparing to make a similar leap into the cosmos. These initial launches focused on the core challenge of escape velocity, clearing the atmosphere and reaching a stable orbit. That proof arrived in 1957, a polished metal sphere, barely the size of a beach ball, demonstrated that an object forged by human hands could operate in the vacuum of space. From that single satellite, our capabilities grew to include complex manned machines capable of carrying heavy payloads into orbit and returning crews to the surface. Step by step, each successive wave of engineers layered new capabilities onto the last. The void above us ceased to be a realm of theory and became a functional, navigable environment. While we often focus on rovers charting distant dust bowls, the infrastructure right above our heads is what maintains the functions of modern civilization. Look closely at low Earth orbit. This dense web of thousands of satellites acts as an invisible nervous system. It processes the GPS signals that route global shipping fleets, coordinates international financial transactions, and tracks the storm systems that dictate our weather warnings. If this orbital layer were suddenly knocked offline, the ripple effects would be immediate. Supply chains would freeze, communication networks would collapse, and emergency systems would lose navigation. Maintaining a network this massive requires constant supply runs. For decades, the cost of throwing away a multi-million-dollar rocket after a single launch limited the scale of this infrastructure. That bottleneck has now been removed through reusable rocketry. Instead of crashing into the ocean, massive boosters are now programmed to guide themselves back through the atmosphere, descending side by side onto landing pads. This allows the same hardware to be refueled and flown again, lowering the cost of orbital transport. Securing this orbital zone provided the blueprint for our modern systems, but those systems remain physically tied to a single, localized environment. To ensure long-term redundancy, we have to look past the safety of orbit and push into the deeper solar system. The next immediate targets sit tens of millions of miles away: the Moon, and slightly further out, Mars. We have reached out to this zone before, but the Apollo missions were short-duration campaigns. We collected rock samples, left equipment, and returned to Earth within days. Current mission architectures focus on building pressurized habitats and power grids capable of supporting humans for years at a time. These designs are being physically tested by teams on Earth right now. Robotic units are forging habitat modules. Artificial intelligence labs are simulating life support variables. And structural engineers are stress testing new materials against extreme atmospheric pressures. The push to become a multiplanetary species has matured into an active industrial operation, supported by long-term funding and hardware testing. But the distance between an industrial blueprint and a successful planetary landing is vast. The deeper we venture outward, the more the laws of physics challenge our survival. The first major hurdle sits right at our doorstep: the Kessler syndrome. By building out our low Earth orbit infrastructure, we've also left behind thousands of dead satellites and spent rocket stages. This creates a high-speed trap of metal fragments that could eventually block our path to the stars. If a spacecraft successfully navigates that debris field, it then faces an exposed void. A transit to Mars requires coasting through deep space for at least 7 continuous months. Out in this open stretch, astronauts are stripped of Earth's protective magnetic field. They are exposed to sudden, violent solar storms and a constant barrage of deep space cosmic radiation that pierces through standard spacecraft holes. Surviving these prolonged exposures requires the development of new shielding technology: heavy water barriers, magnetic deflector shields, and radiation-absorbent alloys that are currently being engineered in labs. Designing ships capable of protecting human life across millions of miles is an engineering task too massive for any single country to execute alone. It requires the cooperation of the world's major spacefaring nations. We already have a model for this collaboration. For decades, different nations have pooled their resources, locked their modules together in the vacuum of space, and maintained continuous human habitation on the International Space Station. The physics of deep space are brutal, but they are predictable. Success will depend on maintaining the global stability required to build and launch these systems together. When you travel far enough away from the surface, the context of human activity begins to shift. Astronauts often experience the overview effect. Looking back at a single sphere suspended in darkness, the geographical borders vanish. it becomes clear that every person alive shares the same localized lifeboat. The question for this century is whether we will stay confined to this single lifeboat, or if we will manage to establish presence on other worlds. The 60 years of data gathered by robotic scouts and orbital stations are now being used to finalize the maps for the first human arrivals. Our hardware and artificial intelligence will chart the course, but the motivation driving us outward has never changed. It is the curiosity that drove our ancestors to cross the ocean, simply to see what was on the other side. Which cosmic mystery or planetary target do you want to see us explore next? Drop a comment below with your thoughts. And if you enjoyed this journey, make sure to like the video and subscribe to the channel. The expansion into the solar system is no longer an abstract goal, but a logistical reality defined by scheduled launches and hardware tests. Thank you for watching, and we'll see you in the next one.
Hello everyone, and I'd like to welcome you to American Education Tech. Join me as we latest breakthroughs in science, technology, space, and innovation. Let's get started.